Hi guys, how are you all doing? Today we're gonna start class 10th mathematics, first chapter, real numbers. Let me jump to Incado. Okay, so we are, yeah, okay, right now. Let me erase it. Okay, so first of all, what are real numbers? Before we start on real numbers, I'm gonna just revise you through all the previous collections of numbers. I'm not gonna use the word set because it is not has been defined yet, but they are obviously set, but let's not dwell into it. Let's just simply call them collection. And what do I mean by collection? Is simply grouping. Now also grouping has a different meaning in mathematics. Think of it as a collection of football players, a collection of cricket players, a collection of let's say equipments. Basically, uh, grouping, like collecting them. Uh, with a common purpose. Like when you collect football players, you make sure no, they are players of football, like not tennis players, not cricket players. You are collecting only the players who plays football. So it is not a proper definition of set either collection, but this is basically giving you the idea because I'm not gonna use much more of the word group or collection or set. So I'm just gonna give you a basic definition that you can understand because I don't think it is in the syllabus as of yet. So when I say collection, it simply means grouping, right? Don't overthink it. It is as simple as definition as well. So we have to learn real numbers. But before we dwell into real numbers, let's just start with natural numbers. Now this is basically an abbreviation of numbers. Okay. So what is natural number? Natural number basically means counting numbers. So suppose if I give you a task to count something, how would you start counting? You would start with 1, 2, 3, 4, and then you goes on as long as the number of objects that you have to count get exhausted, right? So that is basically the method of counting. We start with 1 to 3 and then goes on until all the objects are counted at least once, right? So counting numbers are basically natural numbers. So gonna erase this. Count natural numbers are basically counting numbers. What does that mean? It means that it is a collection of 1, 2, 3, and we goes. Like it is very simple to think of. This dot 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 means that we can go as much as we want. Like there is no stopping. There is no step or a particular stage where this numbering or counting can be stopped, right? We can go on to 1000, but then 10,000, then 10 lakh, then to 10 crores, and even after that. So there is no stopping. The simple method is we just have to count, we just have to add one more from in the previous number. So suppose there is 1, we have to add 1 plus 1, and we will get 2. Then uh, the number previous to this number is 2. So if we add 2 plus 1, we are gonna get 3. In the same way, we can just add 1 more in each previous number. We will always get a number and there will be no stopping it. So this symbol simply means this dot dot annotation simply means that we can go on forever and there is no stop, right? And these brackets are simply I'm using them to uh, define that this is the opening of the collection and this is the end of the collection and everything in between them is the element of that particular collection. Okay, so this is natural numbers. Now what are whole numbers? What are whole numbers? So just think of it like when we started counting, we started from 1 to 3, right? And we goes after it, like forward in the right direction. But what if the number of objects we are supposed to count has no objects? So we had defined that if we have to count something, and if there are no, if we have to count a number of objects and there are no number of objects, then this entity, no number of objects, in counting it is said to be zero, right? So if we just add zero along with the natural numbers, that means if we just add, suppose this is natural number 1, 2, 3, and it goes on. If we just add zero into it, the collection that is formed right now, this is simply whole numbers. Then let's just move to, I think, integers. Okay, let's just go to integers. So what are integers? Now, to give you the definition right away, integers basically means all the whole numbers and the negation of all the whole numbers. Now, when I say negation, what does that mean? Let me explain. So suppose you had a simple example, 5 oranges, and you gave up 3 oranges to someone. So how many oranges you will be left with? It will be 5 subtraction 3, which is equals to 2. Now this minus 3, this minus 3 is nothing but this is negation of number, yeah, negation of whole number 3. When I say negation of whole number 3, which what I mean is that suppose if I have to find out that what will be the negation of number 3. So I will write it like this: 3 plus x. Now x will be the negation. I don't know what it will be. Suppose if I don't know. So the definition of a negation of one number is simply gonna be 3 plus x should be equal to 0. So x would be what? 0. And when 3 will move from right hand side to, sorry, left hand side to right hand side, what it will do, right now it is having the plus sign. So when it moves to the right hand side, it will occur a negative sign. So 0 minus 3 is going to be what? Minus 3. That means negation of 3 is minus 3. This is the definition of negation. If I have to find what will be the negative of whole number 3, what I'm going to simply do, I'm going to just write this equation: 3 plus x is equals to 0, and then I will find the value of x. So integers, I'm going to rub it now. Okay, so what it simply means that we're going to take all the whole numbers, that is 0, 1, 2, 3, and then we're also going to take the negatives, the negation of all these numbers. What does this mean? What will be the negative of 1? 1 plus x should be 0. That would mean x should be 0 minus 1. That will give us minus 1. That is minus 1. In a similar way, negative of minus 2 is going to be, sorry, negative of 2, negation of 2 is going to be minus 2. In the similar way, minus 3, and this will go on, right? Okay. Now we have learned up to integers. There are also two collections: prime numbers and then there are composite numbers. Composite numbers. So what are prime numbers? Prime numbers by definition means a number which has only two factors. One factor is going to be 1 and the other factor is the number itself. When I say factor, what does I mean by factor? So I'm going to explain what does I mean by factor. So suppose if I divide 4 by 2, I'm going to get 2 2s are 4. So I can write 2 times and this will become 4, and then we have to subtract and this will become 0. So if I divide a number, suppose 4, by another number, let's say 2, and if I get remainder as equal to 0 without using the decimal, Okay, I am not using the decimal. Without even referring to decimal, if I get 0 as a reminder, then I see that this number, which is a quotient, sorry, divisor, is the factor of the dividend. So think of it as, in more simplest term, that if I have to say that 6, if 6 is the number, I have to find whether 3 is a factor of 6 or not. Then what all I have to do is to check that does 6 occurs in the table of 3. So because 3 multiplied by 2 equals to 6, that would mean that 3 is a factor of 6. Factor of 6. In the similar way, now think of it as, uh, can you just tell me what that does does number 4 is a factor of 8? If 4 is a factor of 8, then 8 should come in the table of 4. Because 4 multiplied by 2 equals to 8, so 8 do comes in the table of 4, so 4 will be the factor of 8. Basically what I mean by factor is a number is said to be x, a number x is said to be a factor of y if x multiplied by something, a natural number or an integer, gives me y. That means p is said to be factor of q if p multiplied by some key equals q, where q is integer. Q is an integer. If q is an integer, sorry, if k is an integer and p multiplied by k equals to q, then I say that p is gonna be factor of q. This is like the definition. So let's just move on. Oh, wait a minute. So we are here on the prime numbers, right? So by definition of prime numbers, the numbers which only have two factors, 1 and the number itself. So can you tell me how many factors does 2 have? Because 1 2s are 2, that means 1 is a factor. And because 2 1s are is equal to 2, so 2 is a factor. Now, is there any other factor of 2 other than 1 and 2? Think about it and you will find that there are no other factors of 2 other than 1 and 2. So 2 is a prime number. Now think of 3. So 1 multiplied by 3 equals 3 and 3 multiplied by 1 equals 3. Is there any other number whose multiple is going to be 3? Or suppose if there is p and I multiply it with a, I get 3. Is there any number p other than 1 and 3? You will find out there are no other numbers other than 1 and 3 whose multiple is going to be 3. That simply means that 3 is also a prime number. Now think of 4. So 1 4s are 4 and 4 1s are 4. So definitely 1 and 4. Okay, I should rub it. 1 and 4 are definitely the factors. But can you think of any other factor, any other number in which table 4 occurs? If I write 2 multiplied by 2, it is also equals to 4. That means 2 is also a factor of 4. But by definition of prime number, there should only be two factors, 1 and the number itself. Because there are more than two factors other than 1 and the number itself, 1 and the number itself, 4 can't be a prime number. So 4 won't be a prime number. But think of it Does 5 is a prime number? 5 will be a prime number. Then 6 won't be because 2 multiplied by 3 is 6. So there is a number other than 1 and 6 itself whose factor there is a number other than 1 and 6 itself, which is a factor of 6, which is 2. So 6 is not going to be a prime number. 7 will be a prime number. Will 8 be a prime number? 1 multiplied by 8 equals to 8. 8 multiplied by 1 equals to 8. So 1 and 8 both are factors. But because 2 multiplied by 4 is also equal to 8, that means 2 is also a factor. So that means that the number 8 has more than 2 factors other than 1 and the number itself 2. Therefore, it won't be a prime number. Next prime number, not 9, not 10, 11, and then goes on. Now, let me ask you a very simple question. Okay, before that, let me just introduce you to composite numbers too, and then we will see. Okay, I should just rub it. Oh, wait a minute. Why did that happen? 5, right? So I have to define what are composite numbers. So any number which has more than 2 factors is said to be a composite number. So 4 has 1, 4 and 2 is a factor. So 4 will be what? A composite number. Now again 6. 6 has 1, 6, 2 and 3. All 4 are the factors. So 6 will be a composite number. Composite number simply means it has to have more than 2 factors, right? In the same way, 8 is also has 2 factors, 1, 8, 2 and 4. All of these are the factors, so it will be a composite number. Similarly, 9 will also be a composite number because it has factor 1, 9, 3, right? And then 10 will also be a composite number. Why? Because it has factor 1, 10, 2 and 5, right? And in the same way, we will keep on going. In the same way, we will keep on going. But now my question is, we have talked about even like if you let's just think of it that we have taken every number, every let's say every natural number we have taken, like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we are getting the general idea that either a number is a prime or either it is composite. But is it true? Because if you look carefully enough, you will see that we have not talked about one. We have not included one in neither the collection of prime numbers nor in the collection of composite numbers. So the question here is, what actually is one? Is one a prime number or is one a composite number? So to answer this question, we will simply go to the definition of the prime number and composite number. What were prime numbers? Prime number were simply numbers which has only 2 factors, 1 and the number itself. 1 only has 1 factor, 1. You see, when I define the definition of prime number, I forgot to mention, but let me correct it in a more appropriate manner. A number is said to be prime number if it has 2 distinct factors. It has to have 2 factors and they should not be equal because 1 only has 1 as a factor. No other number other than 1 multiplying by another integer gives us 1. Like suppose if I write 2, there is no number key. Okay. There is no number key an integer such that multiplying by 2 gives me 1. Similarly, you could have simply Right, like 5 maybe, and 5 multiplied by k where k is an integer won't give me 1 either. Only 1 multiplied by 1 equals 1. This is the only possibility for 1 to occur, right? So what does this simply means? It means that 1 only has one factors, 1. Because prime number must have two distinct factors, 1 and the number itself. So this doesn't falls into the definition of prime numbers. Now, what are composite numbers? Composite numbers are basically numbers which have more than two distinct factors, right? So 1 only has one factor, so it doesn't have more than two distinct factors, so it won't be a composite number either. So what it will be? Well, simply, it will neither be composite nor it will be prime number. So what is 1? The answer is neither prime nor composite. Okay, let's move on to, I think, integers. Then we had rational number. Okay, rational rational numbers. So what are rational numbers? Let me just define the definition. Don't get too overwhelmed by the definition because it might look a little rough. But let's just see. P, Q, such that P is integer, Q is natural number, now here when I say this actually I'm defining a set here, but set again is a collection. So if you don't know the definition of set, don't worry about it. Just think of it as a collection because set itself is a collection of well-defined and distinct objects. So set itself is a collection. So if you don't know the definition of set, don't get too confused about it. Simply think of it as a set. So think of it as a collection in which the elements I'm taking are of this form. This form. The form is P by Q, where P is an integer and Q is a natural number. Now, because Q is a natural number and 0 itself is not a natural number, that simply means the Q can't be 0. We have we knew this absurdity in mathematics that we can't divide with 0 and equate it to something, right? So whenever we divide with 0, we doesn't get anything in equality. Equality is absurdity here. Absurdity here. What simply absurdity means? Absurdity simply means something that doesn't make sense. Something that seems absurd, like not sensible, seems like it is not right, right? So here we are. Rational numbers are basically collection of all those numbers which are of this form, P by Q, where P is an integer and Q is a natural number. So let me just simply ask you whether they will be classified as rational numbers or not. So suppose I write 3 by, let's say, 7. So 3 is an integer and 7 is a natural number. So 3 by 7 will be what? A rational number. 1 by 2 minus 1 by 2. So minus 1 is an integer, 2 is a natural number. So minus 1 by 2 is going to be what? A rational number. What if I have written it like this? Minus, okay, let's not go with minus 5. Let's say minus 7. Will this be a rational number? Because according to definition, 5 is integer But minus 7 is not a natural number, no? So according to definition, this should not be a rational number, right? But there is more to it. Even if the question is given in this way, we could have simply simplified this as like if the minus sign is, suppose I multiply both numerator and denominator with minus 1. So it's gonna be what? Minus 5. And minus 1 multiplied by minus 7 is gonna be what? 7. Now whatever this is equals to this. So if this is a rational number, then this has to be rational number too. So minus 5 is an integer, 7 is a natural number. That means this is what? A rational number. And if this is a rational number and this is equal to this, then this should be a rational number too. Right? Suppose 2 by 4. Now obviously it is simple, like 2 is an integer, 4 is a natural number. So 2 by 4 is going to be a rational number. But what I would like to explain you here is simply the fact that we could have simply divided both of the numerator and denominator by 2 and we would have gotten 1 by 2, right? So in this two examples, what I tried to explain is that even if the number is given in this form or maybe in this form and we have to judge whether this is a rational number or not, we could do some simplification, right? And if that simplified term is a rational number, then what we have simplified it from, that is the original term, that will be a rational number too, right? There is another definition of rational number, that a number which is either terminating or non-terminating but repeating. And I'm going to tell you what I exactly mean by that. Rational numbers. So there is another definition. Terminating or non-terminating but repeating. Wait a minute. So what does I actually mean? What do I actually mean by terminating? Terminating simply means that when we write a number in decimal expansion, that is when we write it in the decimal form, the decimal form terminates after finite number of terms. For example, 2.001. This is the decimal expansion of a number, and after decimal, the number terminates after 3 steps, right? For example, another example would be 0.334527 So this is a number and this is a decimal expansion, and after 1 2 3 4 5 6 7, after 7 finite steps or 7 finite terms, the decimal actually terminates. So this would be a rational number, this will also be a rational number. When I say non-terminating repeating, so first I will explain what is non-terminating, then I will explain what is repeating and what does both of this combined would actually look like. So non-terminating would mean, suppose you divide 3, suppose you divide 10 with 3. So what would I get? 3 3 is 9, then 1, then we have to use point 0, then 3 is 9, then 1, and then this will goes on. And it will never stop, right? You can do further calculation, you will realize that this will goes on and this won't stop. So this number, this number which goes on forever after decimal and doesn't stop after a finite number of steps of terms is said to be non-terminating. Another example would be 0.1231234 1 2 3 4 5. In the same manner, it's just gonna simply go on. I should delete this. Another set of 6 terms would be 1 2 3 4 5 6, and then 1 2 3 4 5 6 7, and this will goes on and won't stop. So this will also be non-terminating. What does it mean by repeating? You see this number here after decimal, only 3 is being repeated. So this, even though this is non-terminating, but 3 is being repeated over the time, na? Like after decimal, only 3 is the number which is being repeated. No other term is being repeated, only 3 is repeating, right? So this is called non-terminating but repeating. Another example would be, let's say 1.232323. In the same manner, it's never gonna stop. It's always gonna be 2 3 2 3 2 3, but you can easily realize that only 2 3 is being repeated infinite number of times, right? So even though this is non-terminating, this is repeating. If a number is non-terminating but repeating, then what do we say? That is also a rational number. Now, even though this looks like that, why, how can this be a rational number, or how can this be a rational number? Like, even if you find it visually hard to explain yourself, I will just give it a little proof. So let's just look at this example. So we have to prove the 1.232323, which is non-repeating, but non-terminating, but it is repeating. 2 3 is the term repeated over time, is a rational number or not. So let's just assume x is equals to 1.232323, and another way to write a non-terminating repeating number is simply determine the terms which are being repeated. In this case 2 3, has simply put a bar on it. This bar simply means that 2 3 2 3 is the term which is being repeated over the period of time. I shouldn't have used over the period of time. Just let's just simply say that 2 3 is being repeated infinite number of times. So now determine how many terms are being repeated. Here 2 digits are repeated, right? 2 and 3, those are 2 digits which are being repeated over time. So whatever the number of digits that are being repeated over time, we simply have to multiply 10 to the power of number of digits. So here 2 3 are the digit term which is being repeated. So the digit the term contains are 2. So we multiply by 2. X, both sides. 10 to the power 2 multiplied by 1.23 bar. What this will become? This will become 100 x, and what this will become? So suppose if it would have been 1.23 simply, and if I have to multiply by 100, I would have simply write it like this, like I would have simply crossed out the decimal and divided by 100, because 1.23 can be written as 123 divided by 100, and then I would have simply cancelled this two, right? And I would have gotten 123. In the same manner, when I will divide 1.232323 by 100, when we multiply by 100, the decimal, what happens to decimal? It goes behind the number. The number of times, the number of zeros that this term will contain, we will simply have to shift the decimal to those number of digits. So here, when I multiply by 10 to the power 2, that is 100. So 100 has 2 zeros, right? So this decimal will also shift 2 digits behind this number. So it will become 1, 2, 3, 1. But because this number is basically 2323, if point goes from here to here, we will simply get 2, 3, 2, 3, 2, 3, and then this will go on, right? So this is our equation 1, this is our equation 2. Let's simply 2 minus 1. So 100x minus x, like we have to subtract left hand side from left hand side and right hand side from right hand side. So 100x minus x is gonna be what? 99x. And 1, 2, 3. 1, 2, 3.2323, and it goes on, and I'm gonna minus 1.2323. I will simply get 0, 0, 0, 0, and here I will get 2, 2, and 1. So 122.000, because it is a common knowledge that if after decimal only 0 is being repeated, we don't have to write it. So we're going to simply write 122. So x will be what? We will simply divide both left hand side and right hand side by 99. So we're going to get 122 by 9. Because this is an integer, this is a natural number. So this number is what? A rational number. If this is a rational number, then x is a rational number. And we have assumed 1.23 as x. So 1.23 is also gonna be what? A rational number. This is the same way. If three numbers are if a term which contains 3 digits is being repeated over the period over infinite many times, then we will simply multiply it with 10 to the power 3. Okay. So we have rational numbers, terminating, non-terminating, but repeating. Then let me simply add a page. How do I add a page? Okay, so now we're gonna learn what is a irrational number. So what are irrational numbers? Irrational numbers, numbers which can't be. Okay, so we were here, irrational numbers. So what are irrational numbers? Simple definition is if a number is not a rational number, it will be irrational number. So simple definition, not rational, than irrational. If the number is simply not rational, then it will be an irrational number. Or the other definition was of rational number was it has to be terminating or it has to be non-terminating by repeating. So if the number is non-terminating and non-repeating, what I mean by this statement, non-terminating and non-repeating. So number is said to be non-terminating if after decimal it goes on forever, and it is said to be repeating if a particular term containing a particular digits is being repeating. So suppose if both of these doesn't happen, for example 1.23, then 24, then 25, then 26, then 27, 28. In the same way we're gonna go 29, 210, 211, 212, 213, 214. So what I have learned is that this is not terminating, right? It is going on forever, but also not, no term is being repeated, right? Like in the previous example, 2, 3 was being repeated. But if it is 2, 3, then another term 2, 3 has to appear here. But here 2, 3 doesn't appear. So 2, 3 is not being repeated, right? If I assume that 2, 3, 2, 4 is being repeated, then this has to be what? 2, 3, 2, 4. But here I have 2, 5 and 2, 6. That means this is also not the case. So in the same manner, this is non-terminating, but it is also not repeating. This is why this will be irrational. I will simply give you some examples of irrational numbers. Some famous examples. Uh, I should reduce its size a little. Let's say 3. Okay. Examples simply would be these are some famous examples. You might not be able to understand them fully. Maybe I will tell you why they are irrationals. We will prove this, okay, later in the unit. But right now I'm simply going to write it. Wait. Come on, I got it. Okay, this is page number 2. You don't have to tell me again and again. Famous examples would be under root 2, under root 3, then pi or exponential. These are famous irrational numbers. So what does this simply means that they can't be written in p by q form, or simply they are non-terminating when they are expressed in decimal expansion. They are non-terminating and non-repeating. We're gonna prove all of this that they are irrational numbers, but later on in the unit. Right now, just try to remember them, okay? Or if you have to give an example irrational number, you can always form a non-terminating, non-repeating number. For example, 5.23 and 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11. In the same manner, you can form any non-terminating, non-repeating number and it will be a irrational number. But I was trying to give you some famous examples, so these are all the famous examples. We will also know what exactly pi is and what exactly exponential is. Like they are very famous number. Pi is simply formed by like a mathematician observed that like right now I'm not going to give you a proper definition. I'm just going to give you an idea. If you're interested, you can, I will really suggest you and I will actually motivate you to go forward and look for where does the existence of pi and exponential come from. But as of now, I will simply give you some hints that mathematician observed that when a circle, there is a relation between circle and its radius. And no matter how big the circle is or how small the circle is, I can't even draw a proper circle. How small the circle is, the relation between the circle and its radius is always the same. And they found out that there is a common factor by like the relation that is being defined between radius and its circumference cir- circumfer I shouldn't have drawn I shouldn't have written equals to here. There is a relation between this radius and the circumference of a circle, no matter how big the circle is, no matter how small the circle is. And some mathematician has spent their whole life determining the exact value of that factor. That factor itself is pi. And as for the exponential, there were two graphs. Uh, this is gonna be some, I think, 2 to the power x and 3 to the power x. This will, you have to draw this 2 to the power x and 3 to the power x on this simple x and y graph, and you will realize that derivative of 2x, I think derivative of 2x and there is a number between 2 and 3. We don't know the number. That number itself is ex, whose derivative is going to be a new term. And this is exactly why I don't want to tell you all of this, because now I have to tell you what will be the graph of 2x, 3x, then I will have to tell you what actually is the derivative. So I'm just gonna skip exponential. But as for the pi, the idea is this: the mathematician realized that there is a relation between radius and the circumference of a circle. No matter how big the circle is, no matter how small the circle is, there is always a constant factor. By knowing whose value, we can find circumference of circle via its radius, and that factor is pi, and that factor is an irrational number. You can actually look for the known values of pi up to the decimal expansion. It is, I think, in, I don't know exactly what is the number, but it is a very big number and it is still going on, right? Okay, so irrational number happens. Now, what comes next? Real numbers, right? So, what exactly is real number? Real number is simply collection of rationals and irrational numbers. So you simply have to collect all the rational and all the irrational number, and whatever you will get will be the collection of real numbers. So this is the basic meaning of real numbers. Today we have simply learned what are natural numbers, they are counting numbers, then what are whole numbers. If you just include zero with them, they will be a whole number. Then we learned what are integers. So all the whole numbers and the negatives of all those numbers. Negative by definition simply means that if we have to find the negative of 3, then we have to solve the equation 3 plus x equals to 0, and we will get the negative 3. Collecting all the negatives of all numbers, and we will get what? A collection of integers. Then we learn what are prime numbers, a number which has exactly two distinct factors, 1 and the number itself. For example, 2, 3 and 5 and 7. And composite numbers are the number which has more than two distinct factors. For example, 4, 6, 9, 10. Then we learned that 1 is neither prime nor it is a composite number. Then we also learned what are rational numbers. By definition, it is a collection of all those numbers which are in the form of P and Q. Here, yeah. Why did it zoom out? I Okay. Let me just. Oh, yeah, like this. So here, rational numbers are simply P by Q form, where P is an integer, Q is a natural number. Or we can simply say terminating, non-terminating, but repeating numbers. Then we learned that what are terminating numbers. If after decimal expansion, after finite number of term, the decimal expansion actually stopped, right? Or only 0 is occurring after that, then we say it is terminating. For example, 2.001 and then 0.3345279. Or if the number is non-terminating but repeating, that means that 3.333. Now this number is going on forever, right? But because only the term 3 is being repeated time, over the time again, no. Okay, I should correct myself. Only the term 3 is being repeated, right? So this is called non-terminating but repeating. Another example was 1 2 3 1 2 3 4 1 2 3 4 5. So this is a non-terminating and it is non-repeating, right? But if I write 1.232323, then this 23, this term containing these two digits is being repeated infinite number of times, right? And then I actually give you the visualization of how this 1.2323 can ever be said to be a rational number. We simply assume x to be equals to this. Then the number of term which is being repeated, we simply find out how many digits it contains, and then we multiply it by 10 to the power of number of digits on both left hand side and right hand side. We simply solve it. We got x equals to 122, 99. 122 is an integer, 99 is a natural number, so this is a rational number. If this is a rational number and x is equals to this, then x should be a rational number too. Similarly, then we found out what are irrational numbers. So irrational numbers simply are the numbers which are not rationals. Not rationals, या हम लोग ये कह सकते हैं, okay, or we can simply say that non-terminating and non-repeating. So neither they are terminating. So if we write it down in rational decimal expression, they are not gonna ever be stopped. They're gonna go on forever, and they are not gonna be terminating and repeating either. Any no term is being repeated. Famous examples are root 2, root 3, pi, and exponential. Then I simply gave you that how does pi came into existence, and then we define real number. Real number is basically collection of all the rational and irrational numbers. So that is gonna be all for today. I hope you learned something. Try to think about them, these numbers. Try to think about the collection. Let me give an activity for today. If you come across any number today, no matter when you are exchanging a currency, or maybe you are dialing up on a phone number, or maybe you are dialing up a channel number in your TV, whatever the number you come across, try to find out that what exactly the number is. Is that number a natural number, a whole number? These are rational, irrational, prime. At the end of the day, I'm gonna assume all of them are gonna be real numbers, but try to find out that what exactly they are, like what specifically they are. Also, focus on what numbers are prime number and what are composite number, and maybe we're gonna meet again. Thank you, and please subscribe.